right, today we're going to conduct our third and final hypothesis test for the population portion P. So you saw that we ran a left tail test, we ran a right tail test. Now we should probably expect that we're going to be running a two tail test. So here's the question, or here's the problem. An adoption agency wants to investigate if the proportion of all children that is adopted within 1 year after arriving has changed from 3 years ago when that proportion was 0.24. So I want to point something out to you. It says has changed, right? Or is different from, not equal to. And so what are we doing here? We're just concerned, it doesn't matter if it's greater than or if it's less than, it's just that if it's significantly different, right? And so, we're clearly running a two-tail test here, okay? So the agency randomly selects 150 children, 45 were adopted within 1 year, run this test at a significance level of 5%. So maybe I should have stated this before, but that means alpha, our significance level, is what? 0.05. Because we're going to have to compare this with our p-value, which is also a decimal. And so maybe we'll just convert our significance level of that's a percentage into a decimal right now. How do we know that we're conducting a hypothesis test? Well, clearly it says run this test, right, at a significance level. So once you see significance level or alpha and conduct this test, hypothesis test, not a confidence interval. All right, what was the variable? Was a child adopted with 1 year after arriving? Yes, no. Categorical, it's non-numerical. That means we're running proportions. That's why we're testing the population proportion P. What was our sample? 150 children, okay, at this agency. Okay, 150 children. So what's the population of all the children at this agency? And then what would be a success? And this is a really good thing, finding a child that was adopted with 1 year after arriving. Okay, that would be a success. Why? Because we're trying to figure out the proportion that was adopted within 1 year after arriving. Okay, and how many successes did we have? We had, it looks like, 45. Okay, there's X. And that means if we take X over N, that's P hat. So the sample proportion, the proportion within our sample that actually got adopted within 1 year after arriving at the agency was 30% or 0.3. So 45, right? 45 divided by the 150. So hopefully you still got your calculator out and that makes sense to you. Okay? All right. So step one, state the null and the alternative hypotheses, right? We're going to start with the alternative. Think about what it is. Think about, you know what, maybe it's time for you to pause at each step and see if you can start to come up with these answers, okay? Start with the alternative and then go back to the null. When you're ready, start the video again. All right, so this is, we decided it was a two-tail test, right? And 1 year after it has changed from what? When the proportion was what? 0.24. And so P is not equal to 0.24 for the alternative. Okay, or you can say P is not equal to 24%. It's up to you. The null hypothesis would be P is equal to 0.24, all right? And, or you could say equal to 24%, but clearly P sub 0 is 0.24. So that value right there is P sub 0, okay? So that means we're running a two-tailed test, and we are testing both less than and greater than at exactly the same time. Okay, we just want to see, has things changed? Okay, doesn't matter if it's less than, doesn't matter if it's greater than. Is it significantly different? Okay. All right, so check the conditions. All right, and so random sample, and let's see, randomly selects. Okay. Obviously, we could also have it from an experiment. Verify the central limit theorem. Okay. Make sure that the sampling distribution of P hat is approximately normal. All right, and so I'm just going to keep on reminding you this, is that for a hypothesis test, it's this criteria, okay? For confidence intervals, it's this one. Okay, we're going to have to do some calculating. So N times P, we're going to have to do that calculation. So let's see, what do we got? 150, right, times 0.24. That was the value in the null hypothesis, P sub 0. And hopefully you got, on your calculator, 36, okay? That's certainly greater than or equal to 15, check mark. Do the next calculation, 150 times 1 minus P sub 0, we get 114, at least that's what I got. That's greater than or equal to 15, check mark. Okay? What does that mean? Since both are greater than or equal to 15, the central limit theorem applies, and the sampling distribution of p hat is approximately normal. Okay? So that means we can use the formula for what's it called again? The test statistic, right? So we're going to calculate the test stat. There's our formula for the test stat. And I think we have everything. Let me remind you of everything. Here's p sub 0, that's 0.24. Okay? P hat was equal to 0.3. Put this stuff in the calculator, all right? Oh, I'll tell you what, why don't you pause the video, write it down, calculate it out, see if you get what I get. And then once you calculate it out, come back and see what the answer is. So, hopefully you've calculated it. I got here 0.3, 0.24, remember 0.24 down here, and then we got 150, okay? When I calculated it out, I got 1.72 for your test stat. So, what does that mean? Let's do the interpretation of the test statistic. Okay, why did we do it? What we're trying to figure out is how far away p hat is from the null hypothesis. If it's really far away, we're going to reject it. If they're kind of close, okay, well, I actually haven't told you what we're going to do, but that's what's going to maybe happen here, okay, because we haven't rejected the null hypothesis, okay, and so it's probably going to happen here, but we'll see. So let's interpret our test statistic. That's telling us that the sample proportion p hat is 1.72 standard errors above, because it's positive, right? It's positive 1.72, above the value in the null hypothesis. Okay? What's next? After you calculate the test statistic, you should be calculating the p-value. Let's take a look. Calculate the p-value. What are we going to need? We're going to need our test stat, 1.72. What else are we going to need? You remember? Remember what else you have to look at? You have to look at what's the sign in the alternative hypothesis. And so the alternative hypothesis has a not equal to sign. That means we're running a two-tailed test. Okay, so let's go ahead and draw our standard normal. Here's z, and here's 0. Here's 1, here's 2, here's 3, 1.72, right about here, so we'll draw a line about there. Let's see, we need that error right there, so this is 1.72, but that's the greater than sign part. We need the less than also. So we got to come on this side, and here's a -2, and so -1. I should be filling in my, this is 1, this is 2, this is 3, this is -1, -2, -3, but I just don't want to run out of time, and so I'm not going to fill all those in. It's going to get sloppy anyways, because I can't be too precise there. So we also got to figure out that area, and what do we always know? For the standard normal table, that this area, I know it doesn't look exactly the same, maybe I'll make this one a little bit bigger, that this area is exactly equal to that area, so if we just find 1, we can add it to itself, multiply it by 2, that'll be your p-value, okay? And so, in my opinion, my humble opinion, you should probably just simply look at the -1.72 to figure it out, but I know that sometimes confuses students, so let's just look up 1.72, okay? Here's 1.7, here's 0.02. We see that where that comes together. Oh, I almost pointed to the wrong thing. There we go. All right, now that's not our p-value, right? So we got here 0.9573. Please do not multiply that by 2, because you got to know that the p-value can't be greater than 1. It's a probability, right? It's a probability it can't be greater than 1, okay? But what is that? 0.9573. 0.9573 is the area from there all the way over, okay? 0.9573. Okay, even past this area over here. So that means this area over here is just what? 1 minus that. 0.9573. And so, let's see, this area over here is what? 0.0427. That means this area is what? 0.0427. And I bet you if you looked up a -1.72, you would find that 0.0427 number. Okay? What do we got to do with those two numbers? We got to add them up or take one of them, multiply them by 2. And so what do you get? 0.08. What would that be? 5, 4. I think there's our p-value. So it's taking that area, adding it to that area. Okay? There's our p-value. So our conclusion. So a reminder of the rules there. Okay? And don't ever accept the null hypothesis as being true if you say do not reject the null. So we have to probably talk about it here. Because why? We got a p-value of 0.0854. Okay? And that's greater than the 0.05 of our significance level. Okay? And so what's our rule here? The p-value is sort of high. Okay? And greater than alpha, we're going to say do not reject the null. So the decision about the null, do not reject the null. Okay? So this is probably the most confusing thing about hypothesis testing. What exactly does that mean? Don't complicate it. Okay? Don't complicate it. What it means is this, is that it simply means that when you say do not reject the null hypothesis, first of all, you are not accepting the null. What you're simply saying is that the null statement that is in the null hypothesis is a possibility, but so is the alternative. Both are plausible conclusions, and we don't know, based upon a random sample, which one it is. Researchers run into this problem all the time. They run through their test, they had a hypothesis, they ran through the hypothesis, and they couldn't conclude anything, okay? It was inconclusive, all right? And so, so here, we think both the statements that should probably be statements in the null and the alternative hypotheses are both still possible. They're still plausible at this point. They're still very plausible things, okay? And we don't know which one it is, and that means our results are inconclusive. We don't know, okay? Now, when you reject the null hypothesis, you are pretty sure of what's going on, okay? You have really strong results, okay? When you say do not reject the null hypothesis, you are sort of in this wishy-washy mode at this point. We don't know which one it is, okay? And so our final conclusion is going to be something like this. Now, notice the subtle difference here, okay? We're still going to say something about the researcher's hypothesis, which is the alternative. And what are we going to say here? Well, right now, we're going to say we do not. So before we said we did have strong evidence, all we're going to change now is that we're going to say do not. And I want to remind you of something, is that when you do not reject the null hypothesis, you're going to be saying in the conclusion, we do not have, the nots go together, okay? We do not have strong evidence. We do not have sufficient evidence. We do not have statistically significant evidence. At the 5% significance level, the proportion of all children being adopted in the last 3 years has changed from 0.24. So it's still about the alternative hypothesis, the conclusion, okay? So I know this can be a little confusing for students, and let me kind of do my best for the next minute, try to give you an example. Let's say that we were testing the population portion P, and the null hypothesis had P is equal to 0.5, okay? And we were testing if it was greater than 0.5, all right? And so we get a P hat that turned out to be 0.501. Now, is that overwhelming evidence then that for the entire population that it's definitely going to be greater than 0.5? Probably not, okay? Why? Because it's certainly, if you get 0.501 for your P hat, remember, the population portion B could be a little higher than that or a little lower than that, okay? And so that is not overwhelming evidence that P is greater than 0.5 in that situation. Well, the same is going on here. It's just not far enough away from the value in the null hypothesis that we can conclude anything conclusive, all right? So that's what's going on. If you got any issues with that, shoot me an email and we'll chat about it, okay? So that concludes section 9.2. Next thing that we're going to be testing is the population mean. And obviously we're going to change back over to using the t-table somehow. So I'll show you how to do that. Good day.